Assalamu alaikum friends. I'm Taqdees Siddiqui with Computer Graphics for Bachelor's in Computer Science course being offered by a virtual university, Government of Pakistan. Today is our 43rd lecture. We'll be talking about some lighting implementations using OpenGL today. So let's begin. How do we have a perception of color of things when we look at them? When we look at a physical surface, our eyes' perception of the color depends on the distribution of photon energies that arrive and trigger our cone cells. OpenGL approximates light and lighting as if light can be broken into red, green, and blue components. We have talked about light and interaction of light sources and surfaces in quite detail. Those concepts that we built that are going to really come into play today. We'll be able to make use of those concepts and implement certain lighting models, making use of commands that are available in OpenGL. We have talked about the three components of light sources as well as the surface colors. We have decomposed them or divided them into these three components, the red, green, and blue, from which the name RGB was introduced. So we will be playing with these three components of the lights. We'll try to look at the interaction of light and light sources and the surfaces that use those lights to emit or display different colors. These three components would come handy when we'll be talking about creating light sources as well as talking about associating different properties to surfaces on which light is to be thrown, and then they are supposed to give out specific colors. Thus, the color of light sources is characterized by the amount of red, green, and blue light that they emit, and the material of surfaces is characterized by the percentage of the incoming red, green, and blue components that are reflected in various directions. We did talk about interaction between light and surfaces, and then we were making use of the three components, and then we did come across such examples in which we saw that if a specific component in the incident light is missing, we'll not be able to see that color even if it is present in the surface on which the light is being thrown. So वो वाले तमाम ideas जो हमने theoretically build किए थे, अब उनका एक practical test करने का वक्त आ रहा है. हमने एक example ली थी, आपको याद होगा, जिसके अंदर हमने कहा था कि अगर हमारे पास एक ऐसी surface है जिसके ऊपर green component जो है वो non-zero है, लेकिन जो incident light है उस पर that is having a green component 0, तो overall impact जो होगा उसका ये होगा कि उसमें green color हमें दिखाई नहीं दे रहा होगा. And the color that we will be seeing will have contribution of only the red and the blue components. The OpenGL lighting equations are just an approximation, but it's such an approximation that works fairly well, and it can be computed relatively quickly. And that is what a main problem is whenever we are talking about lighting and application of lighting models onto our scenes. हमने बात कर रखी है कि जब भी हम लाइट कैलकुलेट करते हैं और लाइट का इफेक्ट कैलकुलेट करते हैं ऑन अ सीन, तो हमें तमाम ऑब्जेक्ट्स और उनकी डिफरेंट सर्फेसेस के ऊपर लाइट का इफेक्ट जो है उसको कैलकुलेट करना पड़ता है, और ये कंप्यूटेशन काफ़ी कॉस्टली है इन टर्म्स ऑफ CPU टाइम. Therefore, we keep looking for such ways that can help us minimize this time taken to calculate the lighting of a scene. Efficiency is very important aspect. जब कभी भी हमें रियल टाइम ग्राफिक्स की बात करना होगी तो efficiency becomes all the more important. So बहुत दफ़े ऐसा होता है कि एक बहुत अच्छा लाइटिंग मॉडल या लाइट इफेक्ट कैलकुलेशन की टेक्निक मौजूद होने के बावजूद हम उसे इस वास्ते ड्रॉप कर देते हैं कि वो हमारे लिए प्रैक्टिकल नहीं रहती, एफिशिएंसी हैम्पर करती है. The OpenGL lighting model considers the lighting to be divided into 4 independent components, namely the emissive, ambient, diffuse, and specular light. All these 4 components are computed independently and then they are added together. I hope you would be able to recall our discussion on lighting equation and its composition. We are now going to take a look at a simple example of rendering a lit sphere. We'll be making a sphere which will be all lit, and we'll be able to see the impact of lighting equation Now these are the steps that are required to add lighting to our scene. Define normal vectors for each vertex of all the objects. Now these normals determine the orientation of the object relative to the light sources. This is very important. We have already discussed about it कि जब कभी भी हम लाइटिंग के हवाले से बात करेंगे तो हमें अपने सीन के अंदर मौजूद ऑब्जेक्ट्स के सरफेस नॉर्मल्स की बहुत ज़रूरत पड़ेगी, बिकॉज डिफरेंट टाइप्स ऑफ लाइट सोर्सेज और डिफरेंट टाइप्स ऑफ लाइट्स के साथ जो हम काम कर रहे होते हैं, डिपेंडिंग अपॉन what type of light it is and where it is poised, it is going to have a different impact on different objects. तो ऑब्जेक्ट्स की ओरिएंटेशन बहुत इंपॉर्टेंट हो जाती है. अगर कोई ऐसा ऑब्जेक्ट है जिसकी सरफेस जो है वो कैमरा को, हमारे कैमरा पोजीशन को या पॉइंट ऑफ व्यू को फेस कर रही है और डायरेक्टली उस पर अगर लाइट थ्रो हो रही हो फ्रॉम बिहाइंड आवर पॉइंट ऑफ व्यू, द इम्पैक्ट इज गोइंग टू बी डिफरेंट. और अगर उसी ऑब्जेक्ट की ओरिएंटेशन हम थोड़ी सी चेंज कर दें इस तरह से कि वो फेस हमें नहीं कर रही हो बल्कि फेस किसी और तरफ करना शुरू कर दे, तो फिर उसी लाइट सोर्स का इम्पैक्ट उस पर डिफरेंट हो जाएगा. एंड दैट विल रिक्वायर डिफरेंट कैलकुलेशन, एंड ऑल दोज कैलकुलेशंस मेक यूज ऑफ द नॉर्मल्स विच आर बोथ द सरफेस नॉर्मल्स एज वेल एज एट पॉइंट्स वर्टेक्स नॉर्मल्स, दोनों का इस्तेमाल करेंगे. सो द फर्स्ट स्टेप वुड बी टू क्रिएट, सिलेक्ट एंड पोजिशन one or more light sources. We can always make use of multiple light sources in a scene, but of course remember the caution that the number of light sources have a direct impact on the speed of computation, the efficiency. जितने ज़्यादा हम light sources बढ़ाएंगे, naturally हमारी calculations जो हैं वो बढ़ती चली जाएंगी. जितना बेहतर हम scene को करना चाहते हैं, जितना natural looking उसे portray करना चाहते हैं, उतने हम लाइट सोर्सेज बढ़ा सकते हैं डिफरेंट रिक्वायरमेंट्स के मुताबिक, लेकिन अकॉर्डिंगली वी आर गोइंग टू पे द प्राइस ऑफ एफिशिएंसी. सेकेंड स्टेप इज टू क्रिएट एंड सिलेक्ट अ लाइटिंग मॉडल विच डिफाइंस द लेवल ऑफ ग्लोबल एम्बियंट लाइट एंड द इफेक्टिव लोकेशन ऑफ द व्यू पॉइंट फॉर द प्रोसेस ऑफ लाइटिंग कैलकुलेशंस. So we'll be creating and selecting a specific lighting model to use, and then making use of that model will be defining and calculating the global ambient light which would contribute towards the basic light that would be used to define different objects, although we have already discussed that ambient light does not give us the details of the objects. For the details of the objects to come out, of course, other components will have to join hands with ambient. Next would be to define material properties for the objects in the scene. We have talked about different objects giving us different colors in different lighting situations. And in that we know that there is a role to be played not only by the light, but also by the surface of the object on which it is being thrown. So we'll be talking about some characteristics or properties of the surfaces that can be set, and we'll learn how to do that. And we can always play with properties of the light sources as well as those of the surfaces on which the light is going to be thrown in order to generate the colors or impacts that we really want in the scene. Example 1 that we're going to take a look at now accomplishes these tasks. It displays a sphere illuminated by a single light source. So in order to keep things simple, we are going to start with an example that makes use of only one light source. Although in typical applications we have facility of making use of more than that. That means more than one light sources as well. So let's take a look at this example. We start by including our required include files, header files, gl.h, glju.h, and glut.h. Then we define our init function, which starts by declaring an array, glfloat mat specular. Now this holds value 1.0, 1.0, 1.0, 1.0. All four components are set to 1. glfloat mat shininess, and that holds value 50.0. glfloat light position, and that is set to 1.0, 1.0, 1.0, and 0.0. Then GL clear color is set to all zeros. GL shade model is specified to be GL smooth. This has an impact on the shading model that we are going to make use of. It would be smooth shading. GL material FV, GL front, GL specular, and matte specular are passed to this function as parameters. Then GL material FV is passed GL front, GL shininess, and matte shininess. GL light FV is passed GL light 0, which is our only light source that we are going to use, the GL light 0. GL position, light position. And then we make 3 calls to GL enable. First passing it on GL lighting, then passing on GL light 0, and then finally GL depth test. Then our display function is defined making use of GL clear, specifying GL color buffer bit and GL depth buffer bit as parameters. Glut solid sphere, that's the sphere that we are going to draw. 1.0, 20, 16, the 3 parameters passed, and then called to GL flush. The reshape function, which is always called whenever our window is uncovered or is resized, with the parameters integer width and integer height. GL viewport is defined giving the starting and the ending points, 0, 0 to W, H, W and H typecasted as GL size I. GL matrix mode is set to GL projection, and then we GL load identity, call this function to load the identity matrix in order to nullify any previous calculations that might have been changing our matrix. If W has a value less than or equal to H, that means if width is lesser than or equal to height, then GL ortho is passed the parameters minus 1.5, 1.5 and minus 1.5 times GL float of H divided by GL float of W, and 1.5 times GL float of H divided by GL float of W. So H over W is being multiplied by 1.5 and minus 1.5 respectively. Then minus 10.0 and 10.0 are the last couple of parameters that are passed to GL ortho. We'll discuss them later. Otherwise, if W is not less than or equal to H, then GL ortho is called by passing it on minus 1.5 times GL float of W over GL float of H. Now it is W over H instead of H over W. A second parameter would be 1.5 times GL float W over GL float H, and third and fourth would be minus 1.5 and 1.5, and similarly the next couple of parameters would be minus 10.0 and 10.0. Then GL matrix mode is set to GL model view. Of course, we are talking about modeling and viewing transformations. GL load identity. Now coming to the main function, we have a call to glut init with argc and argv passed as parameters, ampersand argc and argv. Glut init display mode, glut single, glut RGB, glut depth are passed as parameters. Glut init window size is specified to be 500, 500. Glut init window position is specified as 100, 100. Glut create window argv 0, that is called next, and then we call init function. After that, glut display func is called with the parameter display, and glut reshape func is called with the parameter reshape. We have already defined the display and reshape functions. Glut main loop is finally called in order to get the ball rolling, and then return 0. The first thing that we have to do, the first and the foremost thing, is to define normal vectors for each vertex of every object. And we have already stressed the importance of this step, that these normals are going to help us find the orientation of surfaces. Or orientation of surfaces क्यों important है? Because they help us find out how a specific object in the scene is poised or oriented, and thus we can tell what light is going to have what impact on that specific object in that very orientation. और इसके साथ साथ हमें और भी हेल्प मिलती है, वो ये होती है कि हमें पता चल जाए कौन सी सर्फेसेज ऐसी हैं ऑब्जेक्ट की जो कि दीगर सर्फेसेज के पीछे छुप जाएंगी और दिखाई नहीं देंगी, ताकि उनको हम अपनी कैलकुलेशंस के अंदर इंक्लूड ना करें, और हम सिर्फ उन सर्फेसेज की बात करें जो कि विजिबल हैं. सो ऑल द इनविजिबल सर्फेसेज कैन बी डिटेक्टेड making use of these normals. An object's normals determine its orientation relative to the light sources. For each vertex, OpenGL uses the assigned normal to determine how much light that particular vertex receives from each light source. although for simplicity, for the moment, we are talking about only one light source. In this example, the normals for the sphere are defined as part of the Glut solid sphere routine. We have talked about normal vectors. That discussion, if recalled, would definitely be handy right now. Next step was to create, position, and enable one or more light sources. Although today we are going to talk about one light source only. Our example 1 uses only one white light source. Its location is specified by the GL light FV call. This example uses the default color for light 0, GL light 0, which is white. If we want to have a different colored light, then we can use GL light or its variations to indicate that. So for the moment, we'll be using only one light source, and that too would be a white light source. We can include at least 8 different light sources in our scene of various colors. The default color of these other lights is black. Although certain latest implementations support even more than 8 light sources, but nevertheless, you have to keep in mind that the light sources definitely would be adding natural look and liveliness to your scenes, but not without any cost. The cost is, of course, that of cost of computation. We'll have to have some balance somewhere, as we did discuss that whenever we are talking about the quality of image and we are talking about efficiency, we have to have somewhere a balance there where we can say, okay, we can live with this quality and we can enjoy the current efficiency. And if our situation allows us, we can go for even complex calculations, adding more light sources and giving a better look to our scene, but definitely would be requiring more computation time. After we have defined the characteristics of the lights that we want, we have to turn them on with the GL enable command. We also need to call GL enable with GL lighting as a parameter to prepare OpenGL to perform the lighting calculation. So light source जब हम create कर लेते हैं तो उसके बाद उसको enable भी करना होता है. यूँ समझ लीजिए कि हमने light define कर दी कि वो कैसी होगी, उसके अंदर हम कितनी इंटेंसिटी हमें रिक्वायर्ड है, किस जगह पे उसको रिक्वायर्ड है, पॉइज करना ज़रूरी है, मगर उसके बाद उसको ऑन करने के लिए हम GL enable का फंक्शन यूज़ करेंगे. तो जब तक हम GL enable के जरिए से उस लाइट को enable नहीं करते हैं तब तक वो समझ लीजिए ऑफ पड़ी हुई है, ऑन नहीं होगी. Now we'll be talking about selecting a lighting model. The GL light model command describes the parameters of a lighting model. In example 1, the only element of the lighting model that's defined explicitly is the global ambient light. From our prior discussions, you would be knowing that our lighting models include all the 4 different components, not just the ambient, but for the moment, we have only specified ambient. But we can definitely make use of other lights, including diffuse, specular as well. Next is to define material properties for the objects in the scene. As I said earlier, that it's not only the light that is going to give us a specific look of the objects or their surfaces, it is the surfaces and their characteristics as well that play a role in this regard. An object's material properties determine how it reflects light and therefore what material it seems to be made of. Since we are not making use of live materials the way we do in photography, so we'll be modeling, we'll be playing with the conditions, lighting conditions, making use of the concept of creating lights and then setting them and poising them at different positions, and also playing with the characteristics or the properties of the surfaces of the materials or the objects that we are using in our scene. So अगर हमने एक ग्लास टेबल दिखाना है तो डेफिनेटली we'll have to have the properties accordingly set for that material which we want to look as if it was made of glass. And if we want it to be cutting the looks of a formica, we definitely will have to set the properties of the material accordingly. Because the interaction between an object's material surface and the incident light is quite complex, specifying material properties such that an object has a certain desired appearance is an art. So don't be depressed if you initially experiment with this and find out that, oh, you are not able to generate the results that you really desire, because this requires quite a lot of practice and mastering. We'll not be able to learn this overnight. This really is more than science. It's more art than science. So you'll have to acquire it and learn it as an art. Learning what properties have what impact ultimately with what light sources. This would require quite a lot of exercise and experimentation. We can specify a material's ambient, diffuse, and specular colors and how shiny it is. In this example, only these last two material properties, the specular material, color, and shininess, are explicitly specified, and that we did making use of the GL material FV calls. You can go back to the source code and refer to it for better understanding. Next step is creating light sources. Light sources have a number of properties such as color, position, and direction, and all these are important. The next parts of our discussion will explain how to control these properties and what the resulting light looks like. The command used to specify all properties of lights is GL light and its variations. It takes 3 arguments to identify the light whose property is being specified. That's the first one. The second argument is the property that needs to be set, and then the desired value for that property. So we won't have to actually physically create those lights. We'll be creating them programmatically, of course. तो हमने ये सीखना है कि हम GL लाइट को इस्तेमाल करते हुए किस तरीके से लाइट सोर्सेज क्रिएट कर सकते हैं और उनकी प्रॉपर्टीज को सेट कर सकते हैं. प्रॉपर्टी सेट करने के लिए हमें लाइट का रेफरेंस चाहिए. किस लाइट की प्रॉपर्टी सेट करनी है, कौन सी प्रॉपर्टी सेट करनी है, बिकॉज जैसा हमने अभी बात की कि प्रॉपर्टीज के अंदर कलर और पोजिशन ऑफ द लाइट इज ऑल्सो एन एडजस्टेबल प्रॉपर्टी. सो जो प्रॉपर्टी सेट करनी है उसका रेफरेंस और फिर उसको क्या वैल्यू देना है हमें, ये तीनों चीजें हम इस फंक्शन को पास करते हैं, एंड देन वी सेट दोज प्रॉपर्टीज फॉर द लाइट सोर्सेज अकॉर्डिंगली. void GL light I or GL light F, and we pass parameter GL enum light, GL enum pname, and parameter. Void GL light IF V, GL enum light, GL enum pname, and pointer to parameter is passed. Now these functions create the light specified by light, which can be GL light 0, GL light 1, or so on up to GL light 7 if we are talking about 8 light sources available. The characteristics of the light being set is defined by pname, which specifies a named parameter, and for that you can look at the table that we are going to show you next. Param, the parameter param indicates the values to which the pname characteristic is set. It's a pointer to a group of values if the vector version is used, or the value itself if the non-vector version is used. So if we are going to make use of that version with the last letter V, then we are going to have different requirement for the parameter. Actual value can be specified if V is not used, and if V is used, we can always specify a pointer to that value. The non-vector version can be used to set only single valued light characteristics. So there can be certain characteristics that require multiple values. So if that is the case, we'll have to use the vector version of the function. The non-vector function would be used wherever our desired property that we want to set value for requires only one value to set. जहाँ कहीं भी एक से ज़्यादा values की ज़रूरत होगी उस property को set करने के लिए, then we'll be using the vector version of the same function. The table that we are going to take a look at contains default values for pname parameter of the GL light. You can see this table. This contains the parameter name, its default value, and the meaning associated with it. Take a closer look at it and you'll be able to see that the parameter names include GL ambient, GL diffuse, GL specular. They are of the same nature, same kind. Then GL position, GL spot direction, GL spot exponent, GL spot cutoff. These are now of course relating to a specific type of light, the spotlight. GL constant attenuation, GL linear attenuation, and GL quadratic attenuation. Their default values are given and their meanings are given in the table. The nomenclature is such that it also makes sense. We'll be revisiting this table. Please note that the default values listed for GL diffuse and GL specular in this table apply only to GL light 0. For other lights, the default value is 0.0, 0.0, 0.0, and 1.0. For both GL diffuse and GL specular, the same default would be used. Our next example, example 2, shows us how to use the GL light function and its variation. It is about defining colors and position for a light source, which is all the more important for us because having created a light source, we have to tell where to position it, because positioning of the light source is going to have an impact on the way our objects are going to look in the scene. GL float light ambient. Now this one holds the 4 values 0.0, 0.0, 0.0, 1.0. GL float light diffuse, that holds all ones. GL float light specular, which holds again all ones. GL float light position is specified as 1.0, 1.0, 1.0, and 0.0. GL light FV pass the parameter GL light 0. So we are talking about the first light source, GL light 0, which of course is the only light source that we are using for the moment. And then we specify GL ambient and light ambient. So we're talking about the first light, light source 0, and we're talking about its component GL ambient, and the value that we want it to be set to is given by light ambient. GL light FV, again GL light 0, GL diffuse, and the value is specified by light diffuse. GL light FV, GL light 0, GL specular, and the value is specified by light specular. GL light FV, GL light 0, GL position, and the position of the light is given by light position. So that's the way we specify different properties and their values are set accordingly, making use of the GL light FV command. As we can see, arrays are defined for the parameter values, and GL light FV is called repeatedly to set the various parameters. In this example, the first 3 calls to GL light FV are superfluous, since they are being used to specify the default values for the GL ambient, GL diffuse, and GL specular, the 3 components. And now we'll be talking about color. We have talked about color from multiple perspectives, but of course today we are talking about it from the light's color and the surface's colors perspective, and how the 2 colors specified are going to end up creating a specific look for the object. OpenGL allows us to associate 3 different color related parameters: GL ambient, GL diffuse, and GL specular with any particular light. And this we have just seen in our last example as well. GL float light ambient, specified value 0.0, 0.0, 1.0, 1.0. GL light FV, GL light 0, GL ambient, pass it on the values light ambient. Of course, whenever we talk about these 4 values specifying a specific light, for instance over here light ambient, we are talking about the RGBA format. I hope you can recall what that A was. Now position and attenuation is next. We can choose whether to have a light source that's treated as though it's located infinitely far away from the scene, or one that is nearer to the scene. We have talked about this issue earlier on as well, that depending upon where a light source is, it is going to have a different impact on the objects of the scene and vis-a-vis over the whole scene. If we are talking about some light source which is at infinite distance, we said that it is not going to be virtually at infinite distance, it can be approximated to be at infinite distance, just like the sun. Now that is going to have a different impact on objects. But if we are talking about some light source which is part of our scene, which becomes native to our scene, for instance a table lamp, this is a particular example of such a light source which is near to our objects, that can have different impact on the surroundings and the object on which it throws light. An example of a real-world directional light source is sun. So we can have directional lights or we can have positional lights. A directional light, just like sun, is a typical example, is going to have different impact on the look and feel of our objects. Particularly these as opposed to positional, these directional light sources, they are easy to deal with because their impact over the whole scene, all the objects in the scene, is kind of similar. But whenever we talk about such a light source which is part of the scene, a positional light source, that of course is going to have different impact on different parts of the scene. The second type is called a positional light source. Since its exact position within the scene determines the effect it is going to have on a scene, and specifically the direction from which the light rays come, because that is going to be important. For the directional sources, the light rays are going to come from the same direction for all the objects. But specifically for a positional light source, since it is going to be positioned within the scene, the direction of light is going to be different for different parts of the scene. मुख्तलिफ objects के ऊपर इस positional light की जो direction होगी वो different होगी. And then depending upon the type of surface that we are dealing with, of the objects of course, it is going to cut different looks. A desk lamp, as I said earlier as well, is an example of a positional light source. The light used in example 1 is a directional one. So we have not used the positional light, we have used only the directional light, just like that a sun. GL float light position 1.0, 1.0, 1.0 and 0.0. GL light FV, GL light 0, GL position, pass it on GL light position as the third parameter, the value for GL position. As shown over here, we supply a vector of 4 values, x, y, z and w, for the GL position parameter. If the last value w is 0, the corresponding light source is a directional one, and the x, y, z values describe its direction. So if we go back, take a look at the values that are specified for light position. The 4 values, the first 3 of them being 1, and the last, the 4th value, w, is specified to be 0. So whenever w is 0, we know that we are talking about not a positional light source but a directional light source. And x, y and z, these are the values that are going to describe the direction. This direction is transformed by the model view matrix. By default, GL position is always 0, 0, 1, 0, which defines a directional light that points along the negative z-axis. Please note that nothing prevents us from creating a directional light with the direction of 0, 0, 0, but such a light won't help us much. Can you guess what? And if you specify this as direction of the light, the 0, 0, 0, x, y, z specified as all zeros, what kind of direction are we talking about? Direction is determined making use of the point position that we specify and the coordinate origin. And of course, origin is 0, 0, 0. So what are we talking about over here? Next is spotlights. You would recall that we have talked about spotlights with a comment that dealing with spotlights is quite difficult. They're costly lights. But of course, we can make use of them effectively to come up with different effects in the scene which are not possible otherwise. Spotlight, aapko yaad hoga, a cone-like light. We have talked about different parts of this cone, those that are going to be more illuminating areas and those that are going to be less illuminating. We can control different aspects of this light, making use of certain commands that are available in OpenGL. Currently, the illustration that you have is pointing out GL spot cutoff. Now what this cutoff is, we are going to find out shortly. Please note that no light is emitted beyond the edges of the cone. This we have already established about the spotlights. By default, the spotlight feature is disabled because the GL spot cutoff parameter is set to 180. You saw in the last illustration half part of it which was being specified as the GL spot cutoff. Now if that cutoff part, that angle, is 180, what would the whole cone cover? Well, of course, it is going to cover the 360 degrees. So it's not virtually going to be a spotlight. So by default, we don't have it as a spotlight. We can make it look like a spotlight by specifying a different cutoff angle. If we specify the default, which is 180, it is going to be a light which is going to spread in all directions. But if we restrict it to say 90 degrees or 45 degrees, we are going to have the impact or effect of spotlight coming in. But that's the beauty. You can restrict the expanse covered by this light, the area covered by the cone of the spotlight. This is programmable. This value means that light is emitted in all directions. The angle at the cone's apex is going to be 360 degrees. So it isn't a cone at all by default. The value for GL spot cutoff is restricted to being between 0 and 90. Unless, of course, it has the special value of 180, which, as I said earlier as well, is the default value that we play with. Typical values that we're going to use would be in the range of 0 to 90. Now, the following lines set the cutoff parameter to 45 degrees. GL light F, GL light 0. The property is GL spot cutoff, and the value that we provide is 45.0. Please note what version of GL light we are using. We are not using the vector version, because over here we are specifying such a property which would be set making use of only one value. We don't need an array of values or multiple values. So hence we won't be using the vector version, and we won't be specifying pointer to values. Much rather we would be specifying the specific value that would be used to set the property. We also need to specify a spotlight's direction, which determines the axis of the cone of light. So GL float spot direction is used for that. We specify it to be minus 1.0, minus 1.0, and 0.0. And then we set the property accordingly using GL light FV, GL light 0, GL spot direction, and we use the values spot direction that are held in spot direction. And note over here the use of the vector version, because we were not talking about a single value to be used to set the property. Spot direction is given by the three coordinates x, y, and z. So they required three values, and three values were held in an array called the spot direction. So we have passed the pointer to that array as a parameter, as the third parameter. Next is about controlling a light's position and direction. This section explains how to achieve the following three different effects by changing the point in the program at which the light position is set, which is set relative to the modeling or viewing transformations. We have talked about creating the light source, we have talked about setting its properties of light, and we have also set the position. And these are the values which are initially set, and later on they can be changed as well. So we can always have a program that makes use of different commands to change these properties along the way. So we can change the position of the light as and when required. We can change the light itself, the color, the intensity emitted by it. So we will be playing with these parameters, making use of the commands that are available using OpenGL. A light position that remains fixed is one of the options, of course. We create the light, we leave it there for the whole duration of our program, that stays where it is defined and selected. Or we can have the option of a light that moves around a stationary object. We can have the impact of an object which is there and light which just orbits it, and we are able to have different views because of the movement of that light. or we can have a light that moves along with the viewpoint. So we can have the third option, that whenever our viewpoint changes, we can make our light change. So different possibilities are there whenever we are talking about positioning and repositioning the lights. We are going to talk about the first one of these, keeping the light stationary. In the simplest example, of course, as we did in example 1, the light position remains fixed. To achieve this effect, we need to set the light position after whenever viewing and or modeling transformations are used. So whenever we make use of viewing and modeling transformations, we should specifically set our light position to the very one that we selected in the beginning, so that no impact of those computations should have an effect on the position of the light. In example number 4 that you will be having in your notes, the relevant code from the init and reshape routines that might be considered in order to understand this concept. Example 4 is about stationary light source, and it goes like this. We define the GL viewport. Parameters passed are 0, 0, W, H. W and H, of course, typecasted as GL size I. GL matrix mode, GL projection. We set the matrix mode accordingly, and then GL load identity is called, so that we are able to initialize and nullify the impacts of any previous computations that might have been made. And then we test if W is less than or equal to H, and then we are going to call GL ortho with the parameters minus 1.5, 1.5, and minus 1.5 times H over W, and 1.5 times H over W, and then of course minus 10.0 and 10.0. And this would be done when width is equal or lesser than the height. Otherwise, GL ortho would be called with the parameters minus 1.5 times width over height, 1.5 times width over height, minus 1.5, 1.5, and then of course the pair minus 10.0 and 10.0. GL matrix mode is set to GL model view, and then GL load identity is called. And in the later part of init, we can write GL float light position, and that is given the values 1.0, 1.0, 1.0, 1.0. GL light FV for GL light 0 is called to set the GL position at light position. As we can see, the viewport and projection matrices are established first, and then we specify the position of the light. So that's the point, that whenever we want to make use of stationary light, we should set our matrices for the viewport as well as the projections. So modeling and viewing, that should be done, and only then we should specify the light position. Then the identity matrix is loaded as the model view matrix, after which the light position is set. Since the identity matrix is used, the originally specified light position 1.0, 1.0, 1.0 isn't changed by being multiplied by the model view matrix. Then since neither the light position nor the model view matrix is modified after this point, the direction of the light remains as 1.0, 1.0, 1.0. The next that we are going to cover today is selection of a lighting model. You would recall that in our previous discussions about lighting and shading, we have talked about the lighting equation, and we have talked about different lighting models that are available or that can be set up. Using OpenGL, we can make use of these lighting models quite easily and efficiently. So now we are going to take a look at how different lighting models can be used. We are going to take the example of one selection of a lighting model. The OpenGL notion of a lighting model has three components: the global ambient light intensity, whether the viewpoint position is local to the scene or whether it should be considered to be an infinite distance away. This is one of the considerations. We have talked about it earlier on as well. So this would be associated with our global ambient light intensity and the positioning of the light source. Whether lighting calculations should be performed differently for both the front and the back faces of the objects or not, this would be another consideration in the making of a lighting model and the selection of a lighting model. This section explains how to specify a lighting model. It also discusses how to enable lighting, that is, how to tell OpenGL that we want lighting calculations to be performed. The command used to specify all properties of the lighting model is GLLightModel and its variations. GLLightModel has two arguments, the lighting model property and the desired value for that property. So we use this command with these two parameters only. Void GLLightModel, I or F. Parameters are GLEnum pname and the parameter value that we want to specify. And similarly, its vector version, which makes use of the parameter value to be a pointer to values. Now this sets properties of the lighting model. The characteristic of the lighting model being set is defined by pname, which specifies a named parameter for which you can refer to table number 2. Parameter indicates the values to which the pname characteristic is set. It's a pointer to a group of values if the vector version is used, or the value itself if the non-vector version is used. The non-vector version can be used to set only single-valued lighting model characteristics, not for GLLightModel ambient. Take a look at this table 2, which gives us the default values for the pname parameter of the GLLightModel. The GLLightModel ambient, GLLightModel local viewer, and GLLightModel two-side values are given in this table. Next, we have to talk about the calculation of GL ambient light. We'll quickly do that. For setting this, we make use of the command glfloat lmodel ambient, value specified as 0.2, 0.2, 0.2, 1.0, and then we make a call to GLLightModel FV, making use of the parameters GLLightModel ambient and the values contained in lmodel ambient. So lmodel ambient would be the array holding the values that we specify for GLLightModel ambient. So folks, today we have quickly taken a look at different possibilities of using light, making use of the OpenGL. We can define different types of lights, we can create different types of lights, and then we can set their properties accordingly. We have not given a lot of time to discussion on setting the properties of materials, but nevertheless, we have commented that this is an art form. Mastering this is definitely an art. I hope most of you would be already setting out on this road and would be mastering different aspects of making use of OpenGL to generate exciting graphics. Next time, we'll be back with you again with another exciting topic. तब तक के लिए इजाज़त दीजिएगा. फ़ी अमान अल्लाह.